Hey everybody, so today we are finally starting linear regression. We're going to do an introduction to linear regression today, but before that, a couple things to remember. Your blogs, try to get them done by this week. They just have to be done, I would say, before you get started with the next project. So try and finish that by this week. If anyone has any questions about what to do about blogs, let me know. You can submit them on, I've linked the link to where you submit your blog post over here. I can see 4 of you have done that so far, so thank you to you 4. But don't forget to do that. Also, I've gotten some data set questions. I'll talk about data set a little bit when we get more into the material, but again, if you want to work on a different data set, don't forget to let me know. What would be really helpful is also if you tell me which one of the columns you would like to be predicting. So if you want to do your own data set and a couple of people have already sent over some ideas, that would be something that's helpful for me to gauge whether it's going to be a good project or a good idea to work on that or not. Next, for this week and next week, feel free to do your one-on-ones together with your project partner if you'd like. I feel like sometimes if you're working on something together, it makes sense to ask me questions about them together. So if you like to do that, just send each other the Zoom link and that works fine. And then finally, still a couple of you who haven't put your stand-ups for the week, so please do that. Any questions about any of that stuff? I will also update this with some new material with some notes about this week's stuff. All right, then let's get into it. There's quite a bit of theory here, but I'm going to try my best to break this down for you all. So linear regression is part of statistical learning theory. If we just take away what regression is, what statistical learning theory is all about is you're constructing some sort of model to draw conclusions from your data. And we'll look at how we're going to do that in the context of linear regression in a little bit. And then after you construct this model, you can use this model to make predictions. Again, I'll talk about an example, and then in your projects, you'll be doing the same thing as well. As a quick segue in terms of terminology, the difference between a model and an algorithm. So you might have heard the phrase training a model. That's actually what we're going to do for pretty much the rest of this course. We're going to be training models. But what does that mean? So a model trains via its algorithm. So this phase, we're not going to be going into the math of how an algorithm trains and how a model is trained yet. We're going to do that at the very start of phase 3, just because it's very overwhelming. You can sort of think of an algorithm as a series of steps that a model takes to train. If you remember gradient descent, I believe that was in your pre-work, but gradient descent is basically the algorithm that helps linear regression and a bunch of other models to train. So we'll talk about that when we get to it, but just so you know, algorithm is the series of steps that a model takes to train. So while the best model for your data is a regression that has an equation with this form, and we're going to talk about this in a little bit, where you would say, okay, for this data, I want to use a linear regression. That is the model. The algorithm is the process of choosing the right values for your parameters. So later we'll see parameters in a little bit, and then I hope that will make sense when we get to it. Okay, so before introducing our model, and we will do just below, let's talk about our data. And I think this is when I'm going to talk about as well the kind of data that you should be looking out for. So in the context of statistical learning, there's 2 main types of data, or you can group your data into these 2 subsets, your dependent variables and your independent variables. So your dependent variables are the data that can be controlled directly. And in context, I know that doesn't make too much sense yet, but other names for dependent variable, outcome variable, target variable, response variable, and then independent variables, data that cannot be controlled directly, also known as predictors, inputs, explanatory variables, features. So in models, the independent variables are the variables that will affect or lead to a change in the dependent variable. So as you're also thinking about your data set, you have a bunch of features, and one of them will be your target. It's important to also think about the direction of causality here. Basically, your features will affect your target. And sometimes you have to think a little bit about what that means in context, because in a lot of cases, it is kind of interchangeable, but in some it isn't. I'll talk about that in the context of this in a little bit. Graphically, conventionally, the independent goes on the x-axis, and then the dependent goes on the y-axis. So this is an example where we want to look at someone's income depending on their age. So here's a scatter plot where the age is the independent variable and the income is a dependent variable. And in this setting, we want to study if age has an effect on annual income. If we want to see if annual income has an effect on age, then it will be flipped. But in this case, we want to see, okay, for a certain age, what is the predicted annual income? So independent, dependent, usually what you want to predict or what you want to, what you're trying to predict or estimate from your model is the dependent variable because it depends on all your independent variables. So in this context, you're trying to use age as a feature to predict annual income. When I said earlier that sometimes it's interchangeable, sometimes it isn't. In this case, because of the context of age, well, I guess there are some contexts in which you can do that too, but in this case, usually given a person's age, you want to predict their income. And that's the direction of causality there. Maybe your research question is slightly different. Maybe given a person's income, you want to estimate their age, you can do that too, but then these axes will be flipped. Any questions about this setup? Okay, so in the context of your project, the dependent variable, what you're trying to predict, has to be a continuous variable. That's something that's pretty important to note. It should be continuous. Doesn't have to be like in a certain range, or it doesn't have any restrictions on number of values or number of unique values. It just has to be a continuous number, not different categories, not a categorical variable, or not like a string or something like that. So please take note of that if you're picking your own data set. For this project, the provided data set, the target variable or the dependent variable is the price of a house. And the independent variables are your other columns like square footage, number of bedrooms, number of bathrooms, so on and so forth. Okay, so let's talk about linear regression. So a statistical model, and the model in this case is linear regression, defines a relationship between an independent and a dependent variable. So in this case, a linear regression is a straight line. It defines a linear relationship between independent variables and a dependent variable. For today, we're just going to talk about the case where there is one independent variable, but tomorrow, and also for your projects, you'll be dealing with more than one independent variable. We'll talk about that more in context tomorrow. But if you want to start working on your stuff today, a lot of this stuff does apply for when you have multiple independent variables. Okay. So for this plot, we can see that the relationship between age and income can be shown using a straight line, kind of connecting all the individual observations and data. Of course, you cannot draw, there's no way to draw a perfectly straight line through this data, but you kind of want to estimate on average. So this line is our model. The way that you define a line mathematically follows this equation. I know this is kind of small, so let me see if I can zoom in. So this is a formula that sort of defines a line in math. And you can see here, y is usually what we use for our dependent variable, annual income. And x here is what we use for our independent variable, which is the age. And the way that we define a line is we have these beta values, or if you remember from math before, like y equals to mx plus b, y equals mx plus c. I know in different places they use different letters, but same thing, y equals to mx plus b or c. So this is our equation for a straight line, and it does define the relationship between our dependent and independent variables. So this is a model. The algorithm helps us choose what are the best values for beta 0 and beta 1. Like, what is our intercept? What is the best intercept to have? And what is the best slope to have? In your labs, it goes through the mathematical process of figuring that out. Good to go through, but I will say not important because we never have to do that manually ever. So if you want to figure out the theory of what goes behind picking the best beta, you can do that. But I do want to reiterate that it's not super important to know those formulas. So these beta values are known as parameters or coefficients. So if going forward, I mentioned parameters or coefficients, it is basically the parts that make a model, this linear regression model, into a fit model. So we're going to go through this process of model fitting, because when we start with this, we don't know what the best beta 0 and beta 1 values are, right? Maybe we can start with like a bunch of random lines that look maybe like, I don't know, maybe you would think, okay, the line like this might be a little bit better. Perhaps a line like this works a little better. We don't know. Python's going to do it all for us. But through this model fitting step is when Python is basically shifting the line back and forth through gradient descent technically, but it's shifting the line, tilting it a little bit, moving it up and down to figure out what the best fit model is for this data. So that's the process of fitting a linear regression model to our data. I understand there's a lot of new terminology here. It's just a matter of getting used to like saying the right words in the right order, which will come with time. Okay, so here we have our y, our 2 parameters, and then our x. So choosing the best fit line, there's more than one method for choosing these right parameters. I'm not going to go through too much of the math behind it, but we're going to talk about how we evaluate fit. So let me zoom in again. There's more than one method for choosing the right parameters for a linear regression. I believe in your labs, there is a way that you're going to go through like a covariance calculation, and then you actually get you find out what the best parameters there are. The start of phase 3, we'll be talking about the gradient descent method of solving for this. And also there's a linear algebra method for solving this. All different methods, you roughly will end up with the same numbers. But just know that there are different ways that you can get these best beta 0 and beta 1 values. However, the metric that each method uses to determine the best line is the same. It uses this least squared error to determine, okay, what is the best line? Basically, if I have, earlier I had, let me just draw it out again. I have this black line that's here. I also have this green line and this other green line here. How do we decide which is the best line? I mean, sure, you can eyeball it and say, okay, yeah, based on eyeballing it, it looks like, it's roughly this black line is the best, but we want a mathematical metric to determine what the best line is. And the method for doing that is known as least squared. We're going to use the least squared error. So that's where the term OLS, which stands for ordinary least squares, that's where that term comes from. Because the metric that we use to determine how well the line fits our data is through least squared. So we'll get more into this theory next phase, but every model has an associated cost function that its algorithm uses to learn the best parameters. And the cost function for linear regression is the squared error, basically. So what does squared error mean? We have this line and a bunch of data points. What is the error here? The error here is basically the average distance between the points and the line. And typically it's going to do a root mean squared error. So you take all of these errors, square them so that the positives and negatives don't cancel out. Take the error, square it, sum it together, and then take the root. There is a built-in function to do that as well. So don't worry about that either. But this cost function is basically going to see, okay, how much is this error for this black line? And then let's say they're going to do this process over and over again for a bunch of different lines. So for example, let's say I have this red line over here that is also a potentially good candidate for best fit line. What you can also do is measure this error, all the error between the points in the line. And then so you're just going to see which one has the lowest error, and that will determine what your best line is. The process of gradient descent actually does this in a more automatic, efficient way, but we won't talk about that this phase yet. Any questions about anything that I've said so far? Okay.
So we're not we're not, so where the labs are making us write all sorts of functions to do all these calculations, we're not actually going to have to do them.
Yeah, that's right. We don't have to do any of those calculations.
Fun. Okay.
It's always good to know kind of where it comes from, but I understand in like a fast-paced boot camp, it's very hard to like absorb all of that information. So what I myself did and what a lot of like my former students have done as well is, just put a pin in that for now. And then as you familiarize yourself with, just the process of doing the coding portion of it all. And also we're going to be learning a lot of different things. And at any one job, you won't have to use all of it. So perhaps also after you decide on like what kind of thing you want to specialize in, maybe the thing that you want to specialize in doesn't even need linear regression. Then you don't even have to go into it if you don't want to. And that's definitely something that we can talk about when we're nearing the end of the course.
We're probably going to get to this later, but when we predict using linear regression, like it seems like it won't be so accurate because none of these points are really on the line. So like, you could tell me that we're going to get to this later. Just like, what are we going to do about that?
Yeah, you're right. I think that is one of the things that you just have to make do with. Yeah, you're right in saying that like, because this is our best fit line, the next time we want to predict, let's see, the next time we want to predict if someone is age 40, what is their income? It's going to be based on this line. And we would estimate that the income is going to be like what, 42,000. And let's say we have this person here who's 49, right? And this person who's 49, their actual data shows that their income is around what, 37,000, 38,000. But the prediction would give it something much closer to 50,000. There is a pretty big error there. The idea of linear regression is that you're going to have way more data points than this. So that for any one age, let's just say at like 45, there could be people that are like in this range here. And what linear regression will do is it will fit the line to minimize the overall error. But yes, there is always going to be some error. You're never going to be able to perfectly predict.
All right, thank you.
You're welcome. Anything else? All right. Okay, let's continue.
One question.
Oh,
just
yeah.
From the scientific method thing, is that then where back in days of physics experience, I remember, is that where then you throw standard deviations and statistical methods into it to then determine how far off the error is? Because then you can tell whether that particular error in your model is really off because it's so many deviations from the norm, or if it's really close, so then your prediction is a lot more accurate because it, say, has a standard deviation of 1 compared to, say, 2.5.
Yeah, you're right. So we're going to talk about that more tomorrow, but yes, you're going to come up with some overall error for your model. So when we fit this and we get our like root mean squared error for all of these data points, we'll say, okay, this model, it fits to the data, but it roughly has an error of like maybe, I don't know, plus minus $5,000 in this case, roughly. And then you're going to, whenever you get a prediction, you'll just, have that in mind. That like roughly, there is a high chance that it's going to be within plus minus 5,000 of what the actual result is.
There's nothing we can do about that, like you would in a normal scientific experiment where you'd say, well, this didn't work, so run the test again.
I would say
you just kind of have to learn to live with it.
There's nothing we can do about it in a linear regression sense. We are going to talk about, there are some models and neural networks actually. Neural networks have the ability to fit a model to like every data point. It will be able to like, instead of a straight line, it might be able to fit something like that better fits your data.
Okay, so in the case of, say, in our case, from a data standpoint, we look at just the data we're given and we learn to live with whatever error it throws out and interpret it that way. Whereas if, say, you were running a chemistry or physics experiment and you ran the experiment and you got a giant error and you just go, well, we must have done something wrong, and would start over and do it again.
From an experimental standpoint, yeah. For as a data scientist, linear regression is just one of many, many models. And in the next phase, we're going to talk about other models. So let's say linear regression gives you an awful error. We'll be like, okay, well, let's just try a different model then.
Yeah. So in our case,
Unfortunately, yeah.
for today, as it stands right now, we just have to learn to live with it until we learn the other model.
That's correct. So yeah, unfortunately, this coming project, we are going to be constrained by a linear regression, which, I mean, you'll see that within the linear regression, there's still a lot of adjustments that you can make. But yeah, we don't have other models yet. Phase 3, we will be learning like maybe, I think like 10 new models. And so when we get to that, and I know that sounds very intimidating now, but when we get to that, you'll see it's more of like a bigger picture approach to problem solving, whereas here we're constrained by, we're going to use a linear regression to solve our problem. The next project we'll see is we have these 10 models and we have this one problem, and we're just going to be like trying every model, and we will get to that.
So that for this project and this purpose, it's you get a data set, whatever you get, whatever you find out, you get, and you just interpret it from there, essentially.
Correct.
Okay.
And on top of that, tomorrow we'll just talk about some techniques that you can actually, some techniques that we'll be using to adjust our linear regression model. And then so when we get to that, we'll see that, okay, even though we're constrained by linear regression, there's a lot that you can do to potentially make a linear regression work for you. There are a lot of pros and cons to using each kind of model. And then later when we look at this from like a broader perspective, once we talk about other models, we'll get into the pros and cons of using like a different kind of model for a different kind of problem.
Yeah.
Sweet, awesome.
I was gonna say, I think linear regression is usually used in like a time series way. And a good way I think to think about it is to like minimize losses rather than maximize your gains. Justin, if like you're looking at something like stocks, for example, on a weekly basis, a linear regression can help you minimize your losses rather than maximize how much you're actually making by like seeing exactly what the deviation is like on a weekly basis, for example.
Absolutely. I actually have a couple students doing capstone projects, or they just finished their capstone project and they're doing like stock price prediction, and they're using many different things, like their dependent variables. Just as a few examples, some of them are actually using like news sentiment, like the overall like words that people are saying in news articles or in tweets as well. And those are their dependent variables. We'll get to all of these like things much later on, but yeah, finance is a good application of linear regression. Later today, I'll like get into some of the pros and cons of using linear regression over other models, but yeah, all good things said so far. I like John's message in the chat that all models are wrong, some are useful. That's actually a great quote. I also don't remember who said it, but no model predicts with 100% accuracy. That just doesn't happen. But yeah, some are useful, some are not. And we'll talk about for a linear regression, why a linear regression is particularly useful in a little bit. Sweet. Okay. So we've talked about this, and we've talked about how our error of our model can be measured using the error between the point and the line. And the error is also something that the algorithm uses to pick the best fit line. Okay, so even if after picking the best fit line, you do have some errors still. So let's talk about what that means and how we interpret that. Okay, so here, this is the cost function. Basically what I was saying earlier, you're measuring that distance from the points of the line. This is just what it is in mathematical terms. And I just want to point out, just in case like people get confused by all the different Y letters, you'll see that there are many different Y letters. But every time you have the Y with a little like caret on top of it, that's called Y hat. And let me just like circle that. This one is known as Y hat, which is model prediction. Usually anything that comes out from your model has a little hat on it, it's called Y hat. This is YI, this is our observed result. So what this means is they're basically taking for each point, let's say this guy over here has a, I don't know, value of, I'm just gonna make up numbers, value of 15, and then this actual value is 10, but then this predicted value is 12. They're just gonna take this difference and square it. So let's just use, I don't know, let's just use these three as an example. Let's just say here we have a value of 13, here we have 10, and then here we have, I don't know, what's this? Oh, here we have 12, and then here we have, let's just go with 9 for now. So let's just say with this data point, and this data point, the sum squared error is basically 12 minus 9 squared. So that's 9. And then plus 13 minus 10 squared, that's also 9. Plus, let's see what this is, 2. The difference here is 2, so it's plus 4. And then that's, each of these is already squared, just sum it together, and that's our sum of square residuals. And basically we want to minimize that amount as much as possible. All right. So in evaluating our best fit line, there is this metric known as R-squared. So a metric to determine how well the line fits our data is the coefficient of determination, also known as R-squared. We'll actually be calling it R-squared. And with R-squared, there's a bunch of more y's in here. This equation, they're going to have you code it out in one of your labs, but you never really have to code it out for real. I just want to point out that here we have y, our observed value. This y hat is from our prediction, and then there's this y bar. There's this y bar here, which is the average y. And I just want to scroll back up to this over here. So what these different y's are, this y is y. Oops, let me just get the pen back. Okay, here. So this value here is y bar. This value of like 60, this is y bar. Anything that is on this line is known as y hat. And then any data point's actual y value is just y. So coefficient of determination is measuring how much better is your best fit line compared to fitting a straight up horizontal line. So that's kind of what you can think of as coefficient of determination. So for example, you can see that these arrows here, we have this distance here, this orange distance over here. And let's just say this is, I don't know, 15. Let's just say that this is 15. This orange distance is 15. And then this red distance is 5. And so it's just saying that how much better is this error of 5 compared to our worst fit line of 15. That's one way that you can sort of think about R-squared. And there's a formula that goes through it. It's basically taking the sum of the differences between the line and your actual, and then also your actual and your straight across horizontal line. You can go through the calculation of this. You just never really have to. It's automatically given to you. I'll show you in a little bit. So how do you describe this? And this is actually the important part. If you get an R-squared value of 0.85, because they will literally give you that R-squared value when you fit your model, all you have to do is interpret it. Now, how do you interpret that? One of the more formal definitions for R-squared is that if you get an R-squared of 0.85, it says that 85% of the variations in your dependent variable y are explained by the independent variable in our model. So therefore, you can see that this best fitting line still doesn't perfectly fit through all our data points. However, it's saying that, the variation in our y here, 85% of it can be explained by our independent variable x. So whenever you have your model, whenever you run a model, I actually legit want to see every time you run a model, that line of, okay, we have 85% of our variations being explained by our independent variable. If you have multiple independent variables, which we'll get more into detail with tomorrow, same interpretation. Same interpretation. So I know I've thrown a lot of concepts at you all, but is there anything that anyone can think of right now in terms of questions? Because we're going to get into some code. All right. Okay, so there's a couple models that we can use to run linear regression. Today, we're going to talk about one of them, and then we're going to talk about the other one tomorrow. This one is preferred, and I'll show you why. The one that we're going to be using is called stats models. And we saw this a little bit when we were talking about ANOVA, but stats models is the library that we're going to be using to run our regression. So import all of our things. I'm also going to have this very, very simple CSV, which is just a bunch of weights and heights. So very, very quick EDA, a scatter plot of our height versus weight. You can see that, all right, it kind of does look like you can fit a straight line through it. And in this case, very convenient for us. The way that we set up our linear regression model to predict weight with height is like this. Pretty much 2 steps. First, we have our formula that you have to set up. Usually F, you can call it formula. And you have to use this syntax. And this syntax, I kind of mentioned this really quickly last week, but this syntax comes from the programming language R. And it's basically dependent variable, squiggly line, tilde, independent variable. So this is just saying that I'm trying to predict weight using height. If you have more variables, you actually just do plus like variable 2 plus variable 3, but we'll get into that tomorrow as well. So just so you all know. And then the method that we're going to be using is OLS from stats models. As you can see here, I imported OLS from something within stats models, and that's why I can use OLS. But OLS takes in the formula and a data frame, which is pretty convenient. It takes our data frame, and then all we have to do is call this dot fit at the very end. And literally just by putting dot fit at the end, it will do the model fitting process for you. And then finally, you can spit out a model summary. And just like this, we're going to get these results. So this is where some of our stats comes back. You can see that straight off the bat, they give you R-squared, which is pretty neat. R-squared is already calculated for you, which is why I say it's not important to go through all those formulas. R-squared is given to you. And the way that you interpret this, R-squared of 0.955 is saying that 95.5% of the variation in weight can be explained by height, which is neat. So that means we have a lot of the height variance explained. I've also given like this is copied from the labs, but I do want to highlight some of the important things that result from this table. So first of all, the R-squared. Basically, how well is your model fit to the data? 95.5. And then there's also this adjusted R-squared, which I will talk about more tomorrow. But basically, adjusted R-squared is always going to be a little bit lower than your R-squared. And it takes into account if you have more and more variables. And we'll talk about that tomorrow, but not so important for now. R-squared is 95.5. Here, you're using your it'll tell you that you're using your dependent variable as weight. You have your OLS model. We're using the least squared method. That's just something that they print there to show you when this model was run. The number of observations that you have. DF residuals is basically because we have 2 things that we're trying to predict coefficients for, and we'll get into that in a little bit. It's just 20 minus 2. S statistic, which looks familiar because that was what we used for ANOVA as well. Probability of F statistic. The F statistic overall just shows you how the variation between dependent and independent variable are. I wouldn't be too alarmed with like what that number is. I'd be more alarmed if this number here is more than 0.05. So usually this is pretty much a p-value for that F statistic. You want to just make sure that that is lower than 0.05. Log likelihood we'll talk about. We don't really use that number too much. AIC and BIC, we also don't use this too much. We'll actually talk about this more in phase 4. So that's kind of like the summary part. And these are our results. So from the results, we have our intercept and our height coefficients. Now, if you remember like the equation for a line, this is our y-intercept, and this is the slope for height. So the way that you interpret coefficient is just saying that, if with this coefficient of 5.54, this coefficient of 5.54 just says that if I were to increase height by 1 inch, I think in this data set is what they use. If I increase height by 1 inch, weight will go up by 5.539. That's something that's really important to note, because this is what I was talking about at the beginning with statistical learning theory. In statistical learning theory, you can draw conclusions from your data. you can kind of infer relationships from your data. And so the relationship that we've inferred is that height and weight have this relationship. You know, you increase height by 1, weight will go up by 5.539. Other things to note, there's a standard error, which is fine, t-statistic, which is fine. What we will actually be looking at a lot is the p-value here. So with this p-value, I'm going to talk about what this p-value is for. There's a hypothesis. Every time with a p-value, there is a hypothesis. There is a statistical test being conducted. If you are overwhelmed by stats, just know that low p-value is better. We want to have p-values only below 0.05. And we'll see some examples tomorrow where that is not the case, and we'll talk about implications of that. But basically, p-value, we want that to be low. P-value is the probability, and wait, I'll talk about that later when we talk about the hypothesis. And then we also have this confidence interval. This confidence interval is the interval for the coefficient. So they're saying that this coefficient falls within this confidence interval. It is calculated using the standard error. We also don't typically use the confidence interval, but it's good to know what the confidence values are roughly around. So those are the more important things. Mainly R-squared, p-value R-squared, p-value, and coefficient are the most important things that you need from this output. And every time you run a regression, you will have to be interpreting this output to see how well your model is doing. So next I'm going to talk about, and I've given this is from your labs. You'll see this in one of your labs as well. You can, if you want to know what all of those things are, it's all here. I'm going to talk about this hypothesis for what this p-value is referring to. But any questions before I get into that? Okay. So the hypothesis testing for regression. The null and alternate hypotheses are as follows. So the null hypothesis is there is no relationship between the independent variable and the dependent variable. The alternative hypothesis is that there is some relationship between the independent variable and the dependent variable. So if we reject the null hypothesis, meaning that if our p-value is greater than, if we reject the null hypothesis, meaning that the p-value is lower than 0.05, and in this case, we had p-values of pretty much 0, it's saying that we believe that there is a relationship between height and weight. So if we fail to reject the null hypothesis, it means that we believe that there is no significant relationship between dependent and independent variable, and that our slope parameter of m here is not significantly different from 0. So if the m here, our slope or our beta 1 from earlier, if that was 0, that just means that there's no relationship between weight and height. But because it is, an actual number, then there is some relationship. We can also talk about the magnitude of that number. If there's a very small number, so let's just say that this number, if it was 0.001, but the p-value was still 0, it means that there is a relationship and that relationship is 0.001. However, if I had this relationship of 5.539 and I had a p-value of 0.5, which is bad, then I can say that, yeah, there is no relationship. So it's more important, this p-value is still more important than the magnitude of the coefficient. I think when we get to actual examples, we can talk about this a little bit more, but just things to hear and to keep in mind for now.
Is that because if the p-value falls outside of, because of the null hypothesis testing test, because if it falls out of 0.05, it automatically rejects it anyway. And if your slope happened to be, if that number happened to be 0, the coefficient, because it's a straight line, and therefore it can't be touching any points but 1, because the slope of 0 is a straight horizontal.
Correct. Yeah. So yes, correct. If the slope is horizontal, then there is considered no relationship, because then
because it would only touch one point in the it would only touch one point in the data set, and everything else would be above or below. All.
Yes, you're right. It's not so much about the fact that it touches the point or not, is the fact that if our line was horizontal, straight horizontal, no change in X
There'll be no
will
change, yeah.
change Y. Yeah, it's more of that. It's not so much about like what's touching, like how many points the line is touching, but it's just the fact that if I were to change values of height,
It would
my
remain
weight
the
won't
same
change.
because the line is straight horizontal and the value would be the same.
Yep, that's right. Awesome. Okay, so more about p-value. The p-value, wait, we talked about this already. I guess we could do a review of p-value. The p-value basically represents the probability of observing your results or something more extreme, given that the null hypothesis is true. So applied to a regression model, basically very small p-values will indicate that coefficients are statistically significant. And then usually we're going to use that same cutoff value of 0.05. Okay. So with that, let's talk about some assumptions. And this is where it's going to be more relevant to the project. I saw on your stand-ups, a bunch of you are starting with your data cleaning and your EDA, and these will be good things to keep in mind. So regression is a parametric technique, which means that it uses parameters learned from the data. So these coefficient values, these parameters, are learned based on what our data is. If our data didn't look like this line, and let's say it looks slightly different, you'll still get parameter values. But obviously, if our data looked more like, let's see, a quick example. Let's say our data looked more like this. There's still a chance that it'll fit a straight line that looks something like this. But you can see that there are obviously problems with fitting this straight line through this data. Because of the way the OLS algorithm works, it's still going to fit this line, maybe not with the best R-squared, but you know, the parameters are just going to be learned from the data. The algorithm is not going to know, oh wait, yeah, this does not look like it's going to be good for a linear regression. The algorithm is not going to be able to know that. So this is what we call a parametric technique. So here, because of that, certain assumptions must be made. And these assumptions sort of define the scope of regression analysis. And it is kind of mandatory that the underlying data has to first fulfill these assumptions. So if violated, the regression will make biased and unreliable predictions, like that example earlier, right? So yeah, if we had the points that were kind of not on a straight line, but we use that straight line, obviously we would get unreliable predictions. So before even modeling or during your modeling process, it's always good to check for these assumptions. And for a linear regression project, it is pretty helpful that your EDA works hand in hand with confirming these assumptions. So the first assumption is linearity. And the linearity assumption requires that there is a linear relationship between the response variable and the predictor. So basically between height and weight, there should be a linear relationship. So yeah, if we try and fit a linear model to a nonlinear data set, the OLS will fail to capture the mathematical trend, resulting in an inaccurate relationship. For this relationship, if you plot a scatter plot, and you can test for this assumption using a scatter plot. That's usually good enough. As long as it doesn't look like a weird blob or it looks like it's like weirdly curved or anything, especially because you have a lot of data points, a lot of it's going to look kind of clumpy. You can pretty much just use a scatter plot and eyeball, and it is kind of relative to each other as well. So I would say for your project, a good thing to start doing is looking at the scatter plots of the relationship between your dependent variable, your price of your house, versus all of your other variables. So that's something that you can think about and start doing now. For non-linear relationships, you can use non-linear mathematical functions to fit to the data, but we'll talk about that later. So let's say if I did have data points that looked like, let me just draw this again. Let's say I did have data points that looked like this. There are ways that we can actually transform this data to force it into a linear relationship. And there are some implications that come along with that, but we'll talk about that on tomorrow, actually. We'll talk about that tomorrow. So action item for you all for your project that we can do right now, just check for linearity assumption between your Y and all your X's. Okay, so as an extra measure, it's also important to check for outliers because the presence of outliers can have a major impact on your model. Now, what you do consider an outlier can differ based on context. For example, you can see that this outlier kind of biases your line. Because of this one outlier over here, it kind of pulls the line up, whereas normally you would expect the line to just be like that. And you can see that this outlier has really shifted the line up. It is very contextual, so I want you all when you are considering dropping outliers or very extreme values, think about whether you want to consider these values or not. Let's say you have a subset of like super, super expensive houses. Sometimes it makes sense that, yeah, I'm not going to be using this model for predicting expensive houses. We don't need this to bias our data. However, if you want to have a predictive model that can predict for all ranges of housing prices, then it makes sense to account for those as well, just in case that someone wants to price a very luxury home, you might want to keep those in. So things to think about for now. We'll talk about how to actually treat that data later this week, but just things to keep in mind. When you're doing your EDA, I would say a really good thing to do is just literally like write out what you're observing and write out what you potentially might want to do at this stage, especially. Okay, so that was the first assumption of linearity. The second assumption is normality. And this one can be a little bit tricky to know, but the normality assumption states that model residuals should follow a normal distribution. So note that this talks about model residuals, not the distribution of variables. So let's just say we're doing like weight and height. And let me just scroll back up over here. We have weight and height, and let's just do, let's see, df dot height dot plot. Is that, or is it dot hist? I think I want to do dot hist, or I think it's kind. Go to it like that. Okay, cool. So you can see that this is not very normally distributed, but it's fine. This does not have to be normally distributed. Our height and our weight both don't have to be normally distributed for a linear regression. It is the residuals that have to be normally distributed. What I mean by residuals is the line that goes through this. Let's just use this as an example. If you were to take all of the differences between the points and the line and store them as like a, I don't know, like a column in your data, those values have to be normally distributed. So that's something that's important to test for. And there is no way to really test for that until after you run your models. So with these histograms, basically, there are a couple ways that you can check for normality. One is with histograms, next is with QQ plots, and I'll show examples of either. With histograms, you would just take all of your residuals and plot them on a graph. So typically, residuals should be centered around 0. Your residuals should definitely be centered around 0 because your line should fit, and then you should have about an equal amount of data points above and below your line. That's why it's normally distributed. If you have a residual plot that looks like this, it is usually the sign of 1, your assumption is being violated, but 2, it looks like you probably might have outliers that are causing in this case, very high positive errors. We'll talk about more of these, especially when you get to like particular examples. Another way that you can do checking for your normality assumption is through what's called a QQ plot. Now, QQ plot stands for quantile plot, and it's actually quite similar to what we were doing with the Kolmogorov-Smirnov test from before, where it's comparing, it's basically comparing the distribution between your residuals and a normal distribution. So in this case, they're actually standardizing it. Theoretical quantiles basically mean it's a normal distribution. This ordered values is basically your residuals from your model. And if it's all across the diagonal, that's a good thing. If you see data points that go off, and actually, oh yeah, if you see data points that go off like this just means that you have data that looks like this. If one that looks like this, it means that, this is basically your histogram of your residuals, and this is the associated QQ plot. I honestly don't remember what each QQ plot pattern, what that corresponds to. So I've linked an article saying that, okay, if you see a QQ plot looking like this is how you interpret it. So you can also use a Kolmogorov-Smirnov test as well if you'd like. And if your data is not normally distributed, there are ways to fix that, and we'll talk about more of that tomorrow. Okay. So here's just the code for a QQ plot. We had our model from before. You can see that our model was back here that we fit to our OLS. So you can use stats models has this QQ plot. From stats models, you can pull out your residuals from your model, and then you can plot that as a QQ plot there. So for this data, you can see that it's pretty much on the straight line. We only have 20 data points here, so it's a bit hard to interpret, or it's hard to be analytical about that. But yeah, as long as you don't see like blue dots that are like all the way off, like down here or up there, it should be okay. Okay, finally, we have homoscedasticity. Homoscedasticity is a difficult to pronounce word, and it basically refers to the dependent variable being equal across the range of values for the predictors. And so homoscedasticity is, I would say, one that's slightly harder to check for, but you want to look at your residuals in that with regards to homoscedasticity. Homoscedasticity just means equal variance across the range of your predictive values. There are a couple ways to do that. For example, we look at our residuals. Okay, so this is a method that plots all of these graphs, and I'll talk about what each of those graphs are, but the one that you can look at for homoscedasticity is this one, residuals versus height. So let me just box that out real quick. And I am very aware that I'm talking about a lot of like random things that we haven't talked about yet with like very little context. It's just a lot of information today. So yeah, okay. So this is an important one that we can use to check for homoscedasticity. So homoscedasticity, again, is equal variance across the range of values. So residuals versus height. Here you can see this is our height, and residuals are basically our model's errors. We only have 20 points here, so it's a little hard to see. But what we want to see is that these residuals are fairly even across the range of height. So in this case, if we want to like map out where our residuals are, it kind of looks like it's between this band here, which is not good. Hold on, I need to clear my throat for a second. Sorry about that. Okay, so these residuals are not homoscedastic. Ideally, we want our residuals to be fairly evenly distributed across the range of height. So a good plot, a good homoscedastic plot would look more along the lines of this. So we have dots here, we have dots here. As long as it's fairly even throughout, that's a good homoscedastic plot. However, in this case, because we don't have too many data points, we only have 20, our plot kind of looks like this. And this is something that you'll check for after you run your model again. Okay, sorry about that earlier. Any questions about these assumptions? Okay, I would say action items for today that you can start doing on your project are in your EDA, you can start looking for your linearity assumption. That's a big thing. And also just like regular EDA, like just look at the distribution of your variables, even though it's not important that your variables are normally distributed, just look at the distribution of your variables. And that will prepare you for, doing the rest of your project. Cool. Any questions at this point about anything that we've talked about today? Cool. We're really doing a deep dive into regression over today and tomorrow. So tomorrow is going to be actually a lot, but yeah, I'll talk about what each component relates to our project. Any other questions before we close out for the day? Cool. Well, if there's nothing else, I will go and drink a bunch of water. But yeah, if there's nothing else, feel free to reach out to me on Slack. Again, blogs due by the end of the week. If you want to work on additional data sets that isn't the one provided, let me know. And yeah, leave your stand up if you haven't already. All right, if there's nothing else, I will see you all back here tomorrow and we'll get into more regression stuff. All right, have a great day, everybody. Bye.